Integrals are fundamental to many fields of science and are the baseline for every discipline of physics. Integrals are used to convert from forces to energies and speeds to distances of objects. Integrals can even be used to express more mathematically abstract ideas like volumes of higher dimensional shapes, which are useful in advanced physics topics like thermodynamics and general relativity.
As an example, you're in a car going down an empty highway at 100 kilometers an hour for 2 hours. You want to figure out how far you've gone, but how do you calculate it? We can use speed equals distance divided by time and rearrange to solve for distance. All that's left is to plug in our values and see that your distance traveled is 200 kilometers. But where did this equation come from?
Since the highway is empty, you can go the full distance without having to change speeds. Graphing this over time, we get a simple graph that looks like this. This is the same information we had before, but where is our distance traveled? The answer lies between the lines, literally. The area of a rectangle is length times width. Here 100 is our length and 2 is our width. This looks like our equation before, meaning our area is our distance.
But what if the highway wasn't empty and you aren't moving at a constant speed? Our new graph might look something like this. Our equation before only works for constant speeds and is therefore no longer applicable. However, our distance is still just the area under the curve. The method of calculating this area is integration. We can still use our rectangle method, but we will need to split our area into smaller rectangles. Now, notice how our rectangles still don't match very well with our curve. But what if we were to take more rectangles? Like a lot more rectangles. An infinite number of rectangles.
Splitting this region into an infinite number of very narrow rectangles, we can encapsulate our area perfectly. This is the very definition of an integral, summing an infinite number of infinitely thin rectangles over an area. If we zoom in on one of these very thin rectangles, its width is an infinitesimal unit of time, which we call dt. This is the same width of all of our rectangles, while our height is just what our speed is at that time. Adding all contributions together in this notation gives us our area and thus our distance.
We don't have to have speed versus time graphs to make use of integrals. Plotting any two related variables will yield a curve that you can take the area of. These areas can represent useful information about a system. These graphs can be lots of things, such as force versus distance gives energy, or acceleration versus time gives velocity. Even electric field versus distance gives voltage. The flexibility of integrals provides an unparalleled mathematical description of the world around us.
Thanks for watching. Thanks for watching.
Created using Powtoon.